Today's topic is the X-ray emission spectrum of characteristic and Bremsstrahlung radiations. We have already discussed about the interaction of projectile electron with the target element, and we know that it can interact in two ways. It can either emit the characteristic radiations or the Bremsstrahlung radiations. So before going into the details, I would like to recall some basic physics. And you probably know that there are two types of basic X-ray emission spectrum. The one is line and the other one is continuous. So when we talk about the line emission spectrum, remember that it is discrete and it would contain only certain energies in a range. While on the other hand, when we talk about the continuous emission spectrum, remember that it would have all photon energies in a range. Now let's talk about the characteristic X-ray spectrum. You can see that it has a pattern of line spectra having discrete energies, and we already know that these energies are characteristic of the differences between electron binding energies of a particular element. So if we consider the tungsten as a particular element, we can look at the figure below that the lines are presenting certain energy levels. If we talk about the key characteristic X-rays of the tungsten, these are presented by the five vertical lines, each representing the outer shell electrons. It means that outer shell electron can come from L, M, N, O and P orbits. That's why these lines are 5 in number. So their energies will also vary depending on their binding energies. So we can say that these perpendicular lines are actually representing the variable binding energies of the outer shell electrons. The L X-rays, L characteristic X-rays on the other hand are represented by the four vertical lines, and these lines are also representing the varying X-ray binding energies of M, N, O and P orbits. Now the number of photons created at each characteristic energy is different because the probability for filling a K shell vacancy is different from shell to shell. Although filling L shell vacancies generates photons, but their energies are too low for use in the diagnostic imaging. The important thing to remember is that K X-rays are the only characteristic X-rays of tungsten with sufficient energy to be value of in diagnostic energy. The other low energy lines represent characteristic emissions from the outer shell electrons, and they are not useful for the diagnostic imaging. Moving on to the Bremsstrahlung radiation, you can see that it says these energies range from the peak electron energy all the way down to the zero. So we can guess from here that the X-ray spectrum of Bremsstrahlung X-ray spectrum would be continuous because it has a range, it has a higher limit and a lower limit. The second point is also very important, and it says that when the X-ray tube is generated at 90 kVp, Bremsstrahlung X-rays with energies up to 90 kilo electron volt are emitted. Now, what that does it? It means that by increasing the kVp, we are generating high energy Bremsstrahlung X-rays, but by increasing the kVp, we are also increasing the percentage of characteristic X-rays. So we know that above the 70 kilo electron volt that can be controlled by increasing the kVp at the console. We know that if we increase the kVp or kilo electron volt, we are also increasing the probability of characteristic X-ray emission. We can see in this image that the range for Bremsstrahlung X-rays is from 0 to 70 kilo electron volt, and beyond 70 kilo electron volt there is an increased probability of characteristic X-ray emission. Now Bremsstrahlung X-rays have a range of energies and form a continuous emission spectrum. The maximum energy in kilo electron volt of an X-ray is numerically equal to the kVp of operation. So we have already talked about it, that we can control the kilo electron volt voltage of an X-ray by controlling the kilo voltage peak at console. The number of X-rays emitted decreases rapidly at very low energies. Now, an other important thing to discuss here is the relationship of X-ray energy and the wavelength. X-ray energy and the wavelength both have an inverse relation. So we can say that by increasing the wavelength, there will be decrease in energy of X-rays. Now we will discuss about the factors affecting the X-ray emission, and before discussing these factors individually, we will discuss about some terminologies. The first one is integration. What is integration? A process in which the total number of X-rays emitted from an X-ray tube could be determined by adding the number of X-rays emitted at each energy over the entire spectrum. So this is actually a process by which you can determine the total number of X-rays that are generated by the X-ray tube by adding the number of these X-rays over the entire spectrum. Now the shape of spectrum is really very important. Actually it has two components. The one is the area under the curve, and the other one is the position of your X-ray spectrum. The area under the curve actually represents the amplitude, and the direction, or we can say that the position of the spectrum actually determines the positive or negative shift of the X-ray spectrum. So each factor affects the amplitude or the area under the curve and the negative or positive shifts of the spectrum both. Okay, so in general, the shape of an emission spectrum is always the same, but its relative position along the energy axis can change. The further to the right a spectrum is, the higher the effective energy or quality of the X-ray beam will be. The larger the area under the curve, the higher the X-ray intensity or quantity. So the quality or quantity can be predicted by the amplitude and by the right or left shift of the spectrum. It says that the right shift of the spectrum actually determines the effective energy or quality of the X-ray beam, and the area under the curve actually determines the intensity or the quantity of the X-ray. Now we will discuss these factors individually, and the first factor that we are going to discuss is the effect of MA or MAS. So what is actually the difference between MA and MAS? MA actually stands for milliampere, and it is simply the current passed through the filament of an X-ray tube, while the MAS stands for milliampere through filament of X-ray tube multiplied by the time for which this current is passing, which means by increasing the current, that is milliamperes, we are also increasing the time for the current to pass through the filament. It says that if one changes the current from 200 milliamperes to 400 milliamperes, while all other conditions are kept constant, twice as many electrons will flow from cathode to anode, and the MAS will be doubled. So by increasing the current, we are also increasing the time for this current to pass through the filament. This operating change will produce twice as many X-rays at every energy. The X-ray spectrum will be changed in amplitude but not in shape. Thus, the area under the emission spectrum varies in proportion to changes in the MA or MAS, as does the X-ray quantity. We can clearly see in this image that by increasing the milliampere, the area under the curve or amplitude has also increased, or it has doubled. So we have already discussed that if If the quantity or intensity changes, the area under the curve will also change. So we can clearly compare these two curves of current, one showing the curve of X-ray tube generated at 200 milliamperes and the other curve presenting the X-ray tube generated at 400 milliamperes, and there is an increased amplitude of spectrum at 400 mA. What is the effect of KVP on X-ray emission spectrum? It says that as the KVP is raised, the area under the curve increases to an area approximating the scale of the factor by which KVP was raised. The X-ray quantity increases with the scale of this factor. And when the KVP is raised, the relative distribution of emitted X-ray energy shifts to the right to a higher average X-ray energy. So the important thing to remember is that when KVP is raised, it affects both the amplitude, which is the area under the curve, and the position of the X-ray emission spectrum. The area gets doubles by increasing the KVP, while the relative position of the curve at the energy axis shifts towards the right. So the high energy, which is the high energy side. A change in the KVP has no effect on the position of the discrete X-ray emission spectrum. Remember that. That's because in a tungsten nanotube, no characteristic radiation can be produced when KVP is less than 69.5 kilo electron volt. So these 2 points is really important that I have bold. When KVP is increased, it affects both the amplitude and the position of the X-ray emission spectrum. And the second point is that a change in KVP has no effect on the position of the discrete X-ray emission spectrum, and we have already discussed about the reason. We can clearly see in this figure that by increasing the KVP, not only the amplitude has increased, but also there is a shift towards the right side on the X-ray energy axis. You all are already familiar with 15% KVP rule. It helps radiologic technologists to reduce the patient dose by increasing the KVP instead of MAS, because KVP can control the quantity and to the some extent the quality as well. Sorry, the quality and to the some extent the quantity as well. So that's why if we increase the 15% KVP, then that would be equivalent to doubling the MS. And why do we need to increase the KVP? We know about the Alara principle, so we need to maintain it, and also we need to maintain the optical density of X-ray image. And the other important thing is that how do we calculate it? So for example, at low KVP such as 50 kilo voltage, we need to at least increase 7 kVp, which would be equivalent to doubling the MS. And how would we calculate it? We would actually put the factor of 1.15, where 1 is already representing 100 and 15 would be our additional KVP. So by multiplying it with our selected KVP, we can calculate our new KVP. So a 15% KVP does not double the X-ray intensity, but it is equivalent to doubling the MS to obtain a given optical density. So it says that to double the output intensity by increasing the KVP, one would have to raise the KVP by as much as 40% and not 15%. Effect of edit filtration is also very important, as we know that the edit filtration can effectively absorb the low energy X-rays. So what would it cause effect on Bremsstrahlung X-ray emission spectrum? It will definitely reduce the position of X-ray spectrum on the left side as compared to the right side. There would be more high energy X-rays, so the shift would be towards the right, and as it has absorbed less energy X-rays, so there will be reduced shift on the left side. The overall result of added filtration is an increase in the average energy of the X-ray beam, higher quality spectrum shifted to the right, with an accompanying reduction in X-ray quantity, which is the reduced spectrum amplitude. So there will be reduced spectrum amplitude as there will be reduction in X-ray quantity, and there will be the position shift towards the right. We can see in this figure when we used the filtration, the added filtration of 4 mm of aluminum thickness, we can see that the amplitude has markedly reduced, and there is an increased shift towards the right as compared to the added aluminum filtration of 2 mm of thickness. There is an increased amplitude and less marked shift towards the right. Now the effect of target material. The atomic number of the target affects both the number, quantity, and the effective energy, and that is quality of X-rays. The efficiency of the production of bremsstrahlung radiation increases, and high energy X-rays increases than the low energy X-rays. The change in the bremsstrahlung X-ray spectrum is not nearly as pronounced as a change in the characteristic spectrum, because the bremsstrahlung radiations are not of a particular element. These are not of there is not a tungsten involved in bremsstrahlung radiation emission when we talk about its effect. So the overall effect of the atomic number of target material is that the characteristic spectrum would be shifted towards the right, representing the higher energy characteristic radiation. We can see in this figure that when the atomic number of the target material is increased, the amplitude has also increased, and also the position of the spectrum has shifted towards the right. When we use the molybdenum that has atomic number of 42, the amplitude is less, where that is the area that the curve, and the shift towards the right is also less as compared to the gold that has atomic number of 79. The amplitude has markedly increased, and also the shift towards the right. So the last factor which is responsible for the effect of X-ray emission spectrum is the effect of voltage waveform. There are 5 voltage waveforms: half wave, full wave, 3 phase by 6 pulse, and 3 wave by 12 pulse, and high frequency. So actually the difference in the half wave rectified and full wave rectified voltage waveforms are the same, except for the frequency of X-ray pulse repetition. There are twice as many X-ray pulses per cycle with full wave rectification as with the half wave rectification, and the difference between the 3 phase by 6 pulse and 3 phase by 12 pulse power is simply the reduced ripple obtained with 12 pulse generation compared with the 6 pulse generation. Now what is the voltage ripple? If we talk about the voltage ripple, then we can define it as the alternating component of unidirectional voltage from a rectifier or generator. So the low ripple is required for the proper functioning of a generator, and we can say that if we are using 72 kVp on single phase equipment, and on 3 phase approximately 64 kVp, a 12% reduction will produce similar result. And this is the rule of thumb for radiologic technologies, that is based on the relationship between the X-ray quantity and the high voltage ripple. Um, because of the reduced ripple, operation with 3 phase power or high frequency is equivalent to an approximate 12% increase in kVp, or almost a doubling of MAS over single phase power. We can see in this image that when the single phase waveform is used, the amplitude is less, and also the shift of the spectrum towards the right is also reduced as compared to the high frequency or three pulse waveforms are used. There is markedly increased amplitude and also the shift of the X-ray spectrum towards the right.